Hello, everyone. My name is Victor. I'm a machine learning lead at Cloud Office. And I would like to kick off this presentation today with a very big and bold question, which is, how do we feed a growing population without destroying the planet? So let me just give a little bit of context regarding this. So by the year 2050, we're going to need to produce about 100 million tons of additional food to meet the excess demand. Now, at the same time, about 80% of the farmland in the world is being used to feed farmed animals. While this is happening, 2 million hectares of the Amazon forests are being cut down every year to build soy farms. And the reason for building these soy farms is to produce food for livestock. And while all of this is happening, the European Union alone wastes about 126 million tons of food annually. So this system is broken. It's unsustainable. And it's one of the biggest contributors to carbon emissions, which accelerates the whole climate crisis today. So imagine this. What if we could break the cycle? What if we could find a way to produce food without destroying the environment, without deforestation, without inefficient farming practices, and without producing these millions of tons of carbon emissions which are happening every year? So what we are going to show you today is something which is extraordinary. We're going to show you how we can use artificial intelligence to save about 14 million tons of carbon emissions every year. And just to put this in some perspective, because this is just a number, imagine all the cars in Bulgaria. Imagine if we take them off the road. This is the effect that we're going to have just in the course of a single year. And before I dive into these technologies and how this is actually going to work, let's first ask the obvious question. The obvious question is, why is this happening now? Artificial intelligence is not a new technology. A lot of people think that it is because now we're seeing the fruits of it, but this is a very common misconception. The first time artificial intelligence was used as a term was in 1956. So imagine this was before the civil rights movement. This was before the moon landings. This was before, just about the time Elvis made his first record. So it's been 80 years since then. So for the past 8 years, we have been developing this technology, and right now we're just using it to solve global problems. Now, of course, there's a lot of innovations today, such as the transformer architecture behind all of these large language models and AlphaFold, but the truth is that 95% of the AI technologies which are transforming the global economy have been existing for decades. And the answer to why now is actually very simple. We are just now entering what we call the era of implementation. There's two reasons for that. The first one is computational power. Right? According to Moore's law, computational power is something which doubles approximately every 2 years. And this is why the phones that you have in your pockets today have more computational power than the computers that were used to send people to the moon back in 1969. And the next thing, of course, is big data. Right? Data is something which feeds AI algorithms, without which it's impossible. And in the digital world that we live today, we produce about 2.6 quintillion bytes of data. And all of this, the access to data storage and the access to all of this computational power is, of course, allowed by the cloud technologies, which are on the rise today. So this is why we're doing this now. So what happens is that big data and this computational power do not just allow us to use these technologies, but they also allow us to combine them in some very innovative ways. And to show you the technologies which led to the solution which we're going to be presenting today, I would like to take you on a journey back in time and show you what these were and how they are going to fit in the solution that we're going to be presenting today. So first, in the 60s, robotics were first introduced by General Motors. They were a very big game changer because they automated a lot of labor-intensive and a lot of manual tasks, and they were now being performed at unprecedented speeds and accuracy. And some years later, in the 80s, we had these expert systems which were supposed to emulate decision-making, which was done by humans, and they were operating based on simple if-then statements, logical statements, but they were producing a lot of additional efficiency in terms of decision-making and in terms of operations. Then in the 1990s, what happened is that we had more machine learning, which was being used in manufacturing. So now that we could learn from data, computers could learn from the data and use this experience to make predictions about future events. And one of the most prominent applications and manifestations of that was predictive maintenance. So we could predict when a machine should go through maintenance, and on average, this reduced the downtime by about 20%. What happened next is that we had, well, around the same time, in the 90s, we had computer vision as well. So we could interpret visual data. So all these quality inspections of the products that we were doing could now also be performed by computers and by machines. And just to give you an example, Tesla reduced the production errors by 50% just because of computer vision, which was coming. So technology advances more and more and more. Then in 2010s, we had digital twins. So these were replicas of the complex physical systems. So everything which was in the physical world, we could now replicate it in a digital world, and we could use this to optimize all the decisions and to optimize all the operations and to improve production. And finally, we have in 2016, AlphaGo beat the world champion at the game of Go. So I can see a lot of confused faces here. So what does this have to do with manufacturing, and what does the game of Go have to do with saving the planet? And I am going to get to that. But before I do so, now that I've introduced all of these technologies, I would like to also introduce to you the company which is bringing them all together, Nasekomo. Nasekomo is solving one of the biggest challenges of our world today, which is how to produce feed sustainably without harming the planet. So at this point, I would like to introduce Stefka, who is the Chief Digital Officer at Nasekomo. She's going to tell you a little bit more about Nasekomo's mission.
Thanks, Vic. So thanks for having me today. It's a real pleasure to be speaking about those nice and sexy stuff. To give you a bit of a flavor with regards to Nasekomo and what we're doing, for those of you who have not heard about the business, I would start with the statement that there is something unique which is really differentiating Nasekomo from the rest of the insect producers. And what is that? We're not just a biotech company, we're not just a biotech business, but we're also a tech enabler which is really disrupting the entire sector and the industry. What that means? First of all, our circular economy is transforming organic biomass into a high protein throughout the black soldier fly. That's the name of the insect. Other than that, in terms of artificial intelligence, it's important to mention that we're revolutionizing the business throughout the AI technology. And what that means is namely that we're aiming for fully automated AI-driven operations across a global network of smart factories. I should have perhaps pressed this. And what's important to know is that, apologies for that. Okay, we should be here. So what's important to know is that we're synergizing a number of key components, and those are the industrial technology. That's basically the equipment which is managing the process end-to-end. The genetics, here we do have a joint venture company which is taking care of the best genetic selection of the insect. The final product, as I've mentioned, is something which is addressing global challenges. And last but not least, it's the digital solution and anything that has to do with the AI capabilities, which is synergizing all the components, and it's really making the difference. So by 2050, we're expecting a huge lack of animal protein all across the globe. The numbers are saying that it's expected that we're going to lack 100 million tons of animal protein. And to be able to grow animals and produce meat, we basically need the land. And the land is non-existing. So how we do address that challenge? Again, it's through the black soldier fly, which is transforming into a high-quality protein. And this is what we call the 3 Fs. It's the food, the feed, and the fertilizer. That's yet another product which we're producing, and it's used in the agriculture to supply with crucial and key micronutrients that we're basically needing. So that translates into what Victor has been speaking about, into how we do address the global challenges related with the food availability, food quality, and overall sustainability, speaking about the CO2 previously. So let me share a bit of an insight about the insect. That's the fly, basically. The life cycle is really quick. It's 45 days in total, so really quick and short life cycle. And after the mating, the adult fly is laying eggs, which, by the way, are of weight 17 micrograms. Imagine the size here. Then the eggs are hatching, and we come to the phase which we call neonates. And one neonate is approximately 25 micrograms. Then we come to the larvae phase, and that's basically the phase where we transform the body mass of the larvae into the protein. And we have 2 major stages, which we call starter larvae, that's the baby larvae, and the grower larvae, which is a bit bigger. And their weight vary from 10 milligrams to 200 milligrams. So you could do the calculations by your own, and it's obvious that the body mass is changing quite dynamically. So at the stage of the larvae, we do produce the final products, which are, as I've mentioned, the protein meal, the frass, and the insect oil. Another important or curious fact to mention is that one fly, one adult, could lay up to 1,000 eggs. A couple of more important or curious facts are that they don't fly. That insect does not fly. It's a black soldier fly, but in fact it doesn't fly. They spend their entire life in eating. And another curious fact is that they do eat only at the larval stage. So when they go through the rest of the phases from the life cycle, they basically hibernate. And the only thing they need is a nice environment in terms of temperature, humidity, and other factors. Light, for example, they're photophobic. So that they have all the conditions to reproduce. And we basically manage the life cycle end-to-end, starting from the reproduction throughout the growing by the final product production. And this is all being done by leveraging the AI capabilities to any extent you could imagine in terms of data collection, data processing, operations adaptation, predictions, etc. But today we're going to quickly speak about one of the components, part of our AI solution, which has to do with the quality with the quality component. As you can guess, we're having laboratory, which is taking care of assuring the best possible quality. And of course, that relates to the quantity as well. Today we're going to give a glimpse on how we're doing that. So imagine relating all the facts that I've mentioned previously with an AI, so counting or weighting or making behavioral analysis related with the animal behavior. So all that we're doing basically at Nasekomo, and we do believe that only this way we could address global challenges, because the traditional way of producing is not so efficient, effective, and quality enough so that we could produce so much big amount of animal protein. And Victor will be speaking a bit more details with regards to the actual solution. But again, end-to-end, we're aiming for AI native industry, which is bringing much more benefits, not only to our clients, but also to the entire society. Vic, over to you.
Thank you. Okay, so I did mention that we are going to be combining a lot of these different technologies, such as computer vision and the robotics and the expert systems and reinforcement learning, which is the thing which was involved in AlphaGo and these types of algorithms. So where do we start with? So I think the most fundamental concept here and the starting point is the computer vision. So the computer vision opens our eyes and allows us to see what is actually happening, so that based on that we can make some decisions. What you're seeing here, this is an actual picture of some larvae which were in production, and it doesn't tell us a lot of different things. What happens is that now that we can use computer vision, we can extract information which is even invisible to the human eye. So starting with the most obvious thing, of course, we need to identify these larvae. So this is an actual output from machine learning algorithms. It finds where they are, and because of that, we can now count them. We know how many we're getting. So if production is going well or not, if they're replicating well enough, this is something that we can get from the count. Now, if we add some additional information, such as what their size is and whether they're hydrated or not and what their color is, we can also get these small numbers that you see there. These are the weights. So believe it or not, we can actually estimate the weight of something just by looking at a picture of it. And not only that, if we add some additional information, are they moving or not? Are they stressed out? Are they feeling well? Well, you can also get an indication of whether they're healthy or not. And them being healthy is something very important to produce a high-quality product. We want some happy animals that are going to feed the product as well, right? And the green ones are happy here, the red ones are not very happy, and maybe something's wrong with their health, so we know that we need to change something. So all of this is something that we can get from a single picture of a larva. And this is actually the starting point, right? How does this fit into this whole big picture that I was talking about? So, okay, we have all this information. We know what their count is. We know how much they weigh. We know whether they're healthy or not. These are just a few examples, but we can get even more than that. And we also know that we can control this through how we treat these animals, right? There's a lot of things which are under our control. We can control the environment, like what the humidity is, what the temperature is, what we feed them with, what their diet is. All of this is something that we can control and we have an effect on. And these links here, the orange ones, these are the relationships between all these factors and these KPIs that we have. And each of these links is something that can be modeled with machine learning, right? So we can use the factors now to make predictions about the KPIs. So this seems very straightforward and simple, but in biology, it's actually a lot more complicated than that. And one of the reasons is because we also have links between the KPIs as well, right? So for instance, if you have a higher count, what's going to happen is that there's going to be more competition for resources, and this is going to reduce the growth and the mass as well. At the same time, if there's not enough growth, maybe this affects the mortality rates, so this is going to impact the count as well. So it's an intricate web of a lot of interdependencies when it comes to a living organism. right? And that's why this is a little bit difficult, and the output of one model needs to become the input of another. So how do we handle all of this? So this is where these simulations come in place, simulating everything in the digital world. Imagine taking everything, putting it together, linking it together, and making it into a simulation in which everything which happens in the physical world, now we can simulate in the digital world. And this is very important because now we can start experimenting. We can experiment a lot more safely. We can take this digital world, we can see what happens if we tweak the temperature a little bit, or maybe change the diet mix a little bit, and we can see what the outcome of this is going to be, right? So now we have this. But imagine this, the example that I showed you right now shows about 5, 6 different relationships. Now in reality, these relationships are millions, right? And the combinations of things that we can do, like what is the combination between the optimal temperature and humidity and diet and all of these things, the possible combinations are billions, like even trillions. So this is something which is a very, very difficult task. And how do we find the optimal move in a situation in which we have billions of possibilities? Well, this was the same type of question that Deep Blue had to answer when it beat Garry Kasparov in chess back in '97. It's also the same type of question that AlphaGo had to answer when it beat the world champion at Go back in 2016, right? And these algorithms, they didn't have any strategy. We didn't need to tell them, you need to do something specific. They learned by themselves. Like they played millions of games against themselves, and they had a lot of trial and error which was happening, and based on that, they became masters of the game. And imagine this, a game of chess has more, the possibility of moves there is more than the number of atoms in the observable universe. In the game of Go, it's even higher than that. So this is going to be a piece of cake for an algorithm which is like this, even though it's a very complicated relationship. So now we take this simulation, just as we take a game of chess, and we give it to these types of algorithms, the reinforcement learning algorithms, and now it can find the optimal decision for us. Then they feed the expert systems. The expert systems have these high-level strategies. They translate them to specific instructions for each machine and for each robot. Then we have the robotics. The robotics perform all the operations inside the factory. And of course, this results in the happy animals and the insects. And then from them, we take back the information, we feed it back to these digital systems, these simulations, and this whole cycle closes. And in the end, we have happy animals, we have sustainable production, and we have efficiency in everything that we're doing. And this is just covering the insects, right? The whole factory, imagine all the aspects of it. So if you take supply chain management, quality control, predictive maintenance, genetic selection that we do, all of this can be controlled using the same types of algorithms, and this whole factory becomes one giant brain which works autonomously and makes all these decisions, and it makes them really faster and more precise than any human can achieve. So this is why AI is not just enabling, it's not just helping such solutions, but it's also enabling them. And for the final words...
Well, I'm just conscious of time. Thanks for the reminder. Perhaps just a quick reminder about the key messages that we'd like to send today. It's really not a nice journey ahead if we continue living that way. So let's think of the planet, let's think of the sustainability, and let's believe that AI is really improving our lives already. We'll stay to take any questions, but thanks for everything.